So hi everyone and welcome to this session which will be about the climatic generator in advanced design. So my name is Thibaut. I'm a product technical specialist, which means I'm involved in product specification and validation. So for today's webinar, we intend to show you all the possible building shapes that can be handled with the climatic generator in advanced design and on which you will be able to get wind forces and snow actions in a matter of seconds. We'll begin with wind actions, starting from simple shapes like rectangular buildings and then complexifying them with L-shaped buildings, vaulted roofs and even multi-bays. And we'll do the same with snow actions, again, starting from simple shapes up to the most complex ones. We'll also discuss the various accumulations that will be created with advanced design. And then, if we have enough time left, we will discuss various topics and some features that you may not be aware of, like the way we can define openings, the way we handle wind on lattice structures, or some parameters like the return period, again, depending on how much time we have left. So advanced design and its climatic generator comes with multiple available standards like American and Canadian codes or even the Eurocodes, and of course for the Eurocodes you will get access to multiple national appendices like the French one, the Spanish one, even the Polish, the UK one, and so on. So let's begin with wind actions. And let's start with rectangular plan buildings, which are basically the simplest shapes that you may face. You see, for these buildings, here we have a top view, and the vertical walls can be either D and E when they are perpendicular to the wind, or A, B, and C when they are parallel to the wind. And then for the roof, you will find some peak forces in the F and G zones, and then you will have some H, J, and I zones. And for each zone, not only do you have to find out the zone dimension, but also the pressure coefficient, and this is very tedious, especially because you are sometimes given several values for the same zone. See here for F, J, G and H, basically all zones we are getting a negative value and a positive one. That means you have to consider the entire roof being negative, then the entire roof being positive, and then also one side being positive while the other one is negative. So this is only for the external pressure coefficient. And then you have to combine that with the sign of the internal pressure, which can be either positive or negative. So you see, for a single wind direction, you have multiple outcomes to consider. But fortunately, all these outcomes are automatically handled by advanced design. Alright, so now let me show you how wind generation works on a simple plan rectangular building. So in advanced design, you will introduce a wind family. From there you will define the wind parameters. So the main one would be the wind velocity, depending on the region. Then you can introduce some reduction factors like the CSCD or the KDC, which will affect the D and E vertical walls. And yeah, be careful about the return period, that one is important. And the terrain category. So it could be a coastal building or in a more urban area. And from there you will automatically generate all the required cases. So of course we can focus on one. At this point we can even hide the structure, and we can select the forces on walls, And you see you get the expected zones, like this is an X plus wind, so this vertical wall is zone D with a positive 0.7 pressure coefficient. In the back we got E, and on the side we got the usual A, B, and C zones, and same thing on the other walls. And if we check the roof, you will find the peak forces in the corner. You've got the long G zone there. So here, every time you select a load, you can check the pressure coefficient, the naming of the zone. Here we've got a large H, the very long J, and finally the I with a small pressure coefficient. So this is for a lateral wind, and we can also check a front or back wind, where we've got the edge effects there. And then the ABC zones will be parallel to the wind. So pretty straightforward. So advanced design is also able to deal with L-shaped buildings, even though these shapes are not technically covered in the Eurocode 1, and this is why some countries have issued additional rules to the Eurocode 1. For example, in France, they were released in July 2017, and they explain how you can deal with L-shaped buildings. So first of all, for each direction, the engineer needs to consider an equivalent rectangular building. That way, we can estimate the dimension perpendicular to the wind and parallel to the wind. And then for each direction, we have to consider a 45-degree inclination on one side, because when the wind is blowing inside the L, you will get some peak forces there with D zoned on the wall and F, G, and H zoned on the roof. Whereas with a 45-degree inclination on the other side, you will get the usual C and I zone on the roof with smaller forces. Alright, so now let's see wind generation on a more interesting building, like an L-shaped one. So again, you would select wind velocity, carefully choose the terrain category and all the other parameters. And because we've got a complex shape, we should make sure to use the additional rules to properly handle this L-shaped building. So here they are definitely activated, and at this point we just generate the wind. So as you can see, we've got way more cases, because as we've said, when you're dealing with an L-shaped building, you don't just consider the main directions. See, you have to consider the 45-degree deviation around the main direction. So the wind could be blowing inside the L, or it could be there could be some protection from the L could be protected from the wind. So let's check what happens when the wind is blowing inside the L. So this face will be zone D because it's perpendicular to the wind. But because the wind is also blowing diagonally, this face over a certain distance will be zone D as well. See, all this part of the L will be zone D. So let's see if Advanced Design managed to do that. So we will pick a given wind direction. We will isolate it. I will focus on the forces on the walls. At this point I can hide the rest of the structure. So wind blowing inside the L, so this face will be zone D as expected. In the back you've got zone E, but you can see in the L that this face is zone D. And because this face is also 10 meters long, the 10 meters there will be brought back on the face parallel to the wind, and it will be zone D as well. So you see, inside a certain portion of the L, you've got zone D. Just as if it was zone D with a high pressure coefficient. Then on the side we've got A, B, and C. And here we've got A, B, and then you've got a change of zones where it becomes zone D. And after the L, it's reset to zone A and B. So this is for the wind blowing inside the L. But then you also have to consider a 45-degree deviation on the other side. So what happens then is that you will have a shelter effect. You see, so this face won't even be zone D. You will just get the usual A, B, and C zone till the end of the building. So let's see how it is in advanced design. So that's different wind direction. So that's a different load case. And if we check that for focusing on walls again, okay, that here we've got zone D and zone E in the back, and on the sides we've got zone A, B, and C. Continue there till the end of the building. And you will get the same principles on the roof, where depending on the wind blowing inside the L or with a protection, you will get the corner effects, F and G zones, when it's blowing inside the L, but when it's protected, you won't get this corner effect. So, see, to properly handle an L-shaped building, you need to consider way more wind directions with a 45-degree deviation, and advanced design is doing exactly that. And when it comes to multi-span roofs, so first the edge zones, like the F and G zones with the peak forces, will only apply to the very first roof. The other volumes will only get the large H and I zones. And also, after a certain number of bays, like 1, 2, 3, the subsequent bays will see a reduction of their external pressure coefficient. Can be a 20% reduction or a 40% reduction all along. And again, this is automatically handled by advanced design. Alright, so now let's see wind generation on multi-span bays. So if we generate wind there, so you got all the wind directions, so we will focus on a lateral wind, an X plus wind, and we will check the forces on the roof. So you see, as we've just said, these corner effects like F and G zones will only apply to the very first roof there. So FG is only on this part, and then on the other volumes, at some point, we are supposed to apply a reduction on the pressure coefficient. So if we compare the force on this roof with no reduction, and the same here, you see, we actually have a reduction, and then the reduction is applied all along. And we're actually starting from a 0.33, and we're keeping 60% of that, giving us a 0.5 pressure coefficient on the subsequent bays. So this is how you generate wind on multi-span bays for the lateral wind. So of course you've got then all the other wind directions, but these ones are pretty straightforward. Advanced design can also handle vaulted roofs, and in this case the roof will be divided into 3 zones. First A, then a large B zone, and then a C zone. So this is for lateral winds, and then for the other directions, the front and back winds, well, the roof will be affected by the usual F, G, H zones. Alright, so now let's check wind generation on a vaulted roof. So here I should make sure that the load areas on the roof are defined as circular load areas. And then we will generate the wind forces. And if we check in a lateral wind like X plus, with a focus on the roof forces. We will get, as expected, here you got zone A, then you have a long zone B, and finishing with a zone C. So you got A, B, and C, just as expected. So this is x plus wind, you will get the same for the x minus wind, and then you've got the front and back winds. So that would be the y directions. And in this case, you will have, so this face will be zone D, and in the back it would be zone E. And on the roof, you will first get some H zones, like F in the corners. You will have a G, some G zones in the middle. Then you will get the H zones, and then the I zone with minus 0.5 till the end of the building. So again, in advanced design, you got a proper management of vaulted roofs for wind generation. And advanced design is also able to deal with multi-span vaulted roofs, even though they are not described in the Eurocode 1. But to treat them, we are actually combining the principles from vaulted roofs with the principles from multi-span roofs. See, first of all, the peak forces from the A zone will only apply to the very first bay. The other bays will only get the B and C zones. And then after 1, 2, and 3 half bays, we will start applying a reduction on the pressure coefficients. We will only keep 60% of the CPE values. So you see, from vaulted roofs, we are using the A, B, and C zones, and from multi-span roofs, we are applying the reduction of CPE on the subsequent bays. Alright, so now let's check wind generation on multi-span vaulted roofs. So here the load areas on the roof should be defined as circular load areas. And if we generate the wind forces and we focus on x plus wind and forces on roof, like this one, we will see that we're using the principles from vaulted roof combined with the principles from multi-span roofs. So I will just hide the structure at this point. And you see the A zone will only apply to the very first roof. And then you will find some B zones, a very long one, and then a C zone, which will repeat, and then you will get some B zone in the middle, but with a reduction, starting from the 1, 2, and after the third half roof. See, we have a reduction on the pressure coefficient. It's going from 0.9 to 0.5. And that is because we are applying a 60% reduction, and then you will have the same reduced value till the end of the building. So it's a mix of single vaulted roof and multi-span bays. So advanced design is able to properly handle multi-span vaulted roofs, and these for the lateral wind directions, x plus, x minus, but also for the front and back winds, like the y plus and the y minus directions, with the peak forces at the beginning of the roof, and then in the end you get some very long I area. Advanced design can also specifically handle awnings and protruding roofs, which are not the same thing actually. Because in the Eurocode 1, only protruding roofs are covered, which are an extension of an existing roof. Whereas an awning is a separate piece of roof that can be located at any height. And proper design of awnings required a set of additional rules like the ones that were published in some countries like France in 2017 and which are implemented in advanced design. Indeed, for awnings, we should use the net pressure coefficients, CP net, and the awning should be divided into two zones, A on the corners and B in the middle. And on these zones, we should apply first a descending force based on the location, the relative position of the awning, but also an ascending force which will use the dimensions of the awning. And this ascending force can be quite significant, with a pressure coefficient being as high as 1.7 in the extreme case. Whereas for a protruding roof, as explained in the Eurocode 1, we should use the usual CPE values, and we should combine the pressure on the adjacent roof with the pressure from the wall below. And this is why in advanced design you will usually see two forces being superimposed. The one similar to the force on the roof and the one similar to the wind pressure on the wall below. And usually an awning will get bigger wind forces, especially for the ascending winds where the coefficient is so high. But again, this may vary depending on the direction you're considering and also the value of the internal pressure coefficient. All right, so now let's check wind generation on an awning. So here the load area should be given the awning type. And then in its properties you can you will see that the awning will be defined not with the CPE but with the CP net, the net pressure coefficient. You can choose to generate only the ascending or the descending force or both. Usually you need both. And after wind generation, which is instant, you will get all the required wind directions for rectangular plane buildings mixed with the various outcomes for the awnings, because the force can be descending, so you have a descending force on load area 2, which is the awning, and then we will find at some point the same load case but with an ascending force. So this was the case with the descending force on the awning, and then you will have the ascending force on the awning with a high pressure coefficient. And we can see that on the awning we've got an A zone, a B zone. So we got A zones on the sides and then a B zone in the middle. So this is a proper wind generation on an awning. Alright, so now let's compare that with the wind generation on a protruding roof. So here you see the load area is an extension of the adjacent roof. So it should be given the protruding roof property. And then after wind generation, if we check one load case in particular, we will see that the forces on the protruding roof is a combination of zone D, because it's the same pressure as we have on the wall below, zone D, and we also have superimposed another force with a zone H, which is the same as the adjacent roof. So you see, when you have a protruding roof, the wind force is the sum of the wind force on the wall below with the wind force on the adjacent wall. Alright, let's see snow actions now, starting with simple shapes like monopitch and duopitch roofs. So in this case, we've got two snow situations. You have the undrifted snow with a uniform load, and then the drifted snow arrangements where you've got a 50% reduction on one side. Alright, so now let's see snow generation on a simple building. So we'll start with by introducing a snow family. There we will define the snow region and the other parameter like the exposure factor, which will amplify the snow ground load in the absence of wind. You got the thermal factor in case the building is has a heat system, is not properly isolated. In this case, the snow will tend to melt. We have the return period, very important. The altitude, and the generation will be instant, just like for wind forces. And depending on the region that you chose, you might have or not an exceptional snow case. So now if we check, like this is the uniform snow arrangement, it's the same force on both sides. Then you've got the drifted snow arrangement with a 50% reduction on one roof and the other way around, because the snow can be drifted by the wind action from the other direction. And then you've got the exceptional snow load with only the undrifted arrangement. And advanced design can also deal with multi-span roofs, where again you will get the undrifted snow arrangement and also the drifted snow situation, which will result in snow accumulation on the inner base. So let's check that on an advanced design model. So we'll generate snow on this multi-span building. So we got the uniform low rent situation, the same load on all roofs. We got the exceptional one, just higher. And then you've got the drifted snow arrangement. Drifted means you will have accumulation on the inner volumes. So it begins with a uniform arrangement, and then you add the accumulation there in the middle. And you've got it for every inner volume. Advanced design can also deal with vaulted roofs, where we've got the undrifted snow uniform load situation and some drifted snow arrangements, where the roof is divided into 4 lengths and you get 2 peaks there, one peak being 50% higher than the other. And we can also notice that past a 60-degree angle, snow does not apply because it will just slip from the roof. Alright, so now let's check snow generation on the vaulted roof we've used before for wind. So the snow generation is instant. We get the expected cases with first the uniform snow distribution here. So you have the same load on the entire roof. We can see that one portion of the roof is not getting any load because the slope is actually higher than 60 degrees, so the snow cannot stick there, so no snow action on this portion. So this is the uniform, the undrifted snow arrangement. You've got the exceptional one, and then you have the drifted cases. So first case, where the roof was divided into 1, 2, 3, and 4 zones. And you get two peaks, and the first peak is 50% smaller than the high one. And then you've got the other way around. So two peaks, except the maximum peak is on the left side, because the snow is drifted by the wind direction in the other in the other direction. And then we've got the multi-span vaulted roofs geometry that you can handle with advanced design, even though they are not technically covered in the Eurocode 1. But again, we are mixing the principles from a vaulted roof with the principles from multi-span roofs. You see, so first for the drifted snow arrangement, you will get the two peaks on the edge volumes, with one peak being 50% higher than the other, and on the inner volumes you will get the snow accumulation from multi-span roofs. Alright, so now let's generate snow forces on this building, which is made of multiple vaulted roofs. So snow generation again is instant. We get the expected snow cases, starting with the undrifted snow arrangement. And then we've got the drifted snow, where we can see that we've got on the first and last half roofs, we see the two peaks from before, the one being 50% lower than the other, and on the inner base we can see that the snow force gets stronger due to the accumulation that we have on the middle volumes, so here, here and there. Advanced design will also automatically generate all sorts of snow accumulation, whether from a taller building or from a parapet wall, or even the snow accumulation in a gutter. So this gutter accumulation is because when you have a potential snow accumulation and it rains, the rainfall will get trapped inside the snow and it will make snow heavier. So in these areas you have to account for an extra 0.2 kilonewton per square meter load. So this gutter accumulation is because of the rainfall getting trapped in the snow. Okay, so this building is actually the perfect example of all the possible accumulation that advanced design will automatically generate, because I have some parapet walls right there on these load areas here, so they are given the parapet wall property. On this roof I have activated the gutter accumulation, and here I have a taller building, so advanced design will automatically generate the corresponding accumulation. If I just generate the snow, I get multiple cases, starting with the uniform, the undrifted arrangement, so we don't expect any accumulation there. But if I look at the drifted snow arrangement, like this one, so maybe I can display, simplify the display. Here I have the accumulation from the parapet wall over a distance of should be at least 5 meters long. So accumulation from the parapet wall, and here I have a uniform force on both sides. This is a gutter accumulation right there. It should be applied over a 2-meter distance with an intensity of 0.2 kilonewton per square meter. And as for the accumulation from the higher building, I will get it in this case, and these are the huge accumulation there due to the taller building, which was automatically detected. So now let's discuss some features and capabilities from the climatic generator that you may not be aware of. For example, advanced design lets you define openings on the building faces. You may have one face completely open, and in this case, the internal pressure coefficient is easily computed. But you may also have, you may define for each face a certain amount of openings through either an opening ratio or a surface of openings. And in this case, advanced design will first compute the mu coefficient, and from that it will find out the internal pressure coefficient. Right, so in advanced design you can define openings. For example, you can have a face completely open there. And in this case, instead of having for, let's say, this direction, instead of having a zone D with a 0.7 pressure coefficient, so first I won't get any wind force there because the face is completely open, and the internal pressure coefficient will be taken for this direction as 90% of the CPE we don't have. So it will be 0.9 of 0.7. So this is why for this direction we have a CPI, internal pressure coefficient, of 0.63. And if we check another direction, like a lateral wind, it's a bit more complex there, because if we check the other face, the face that we open would have had a mix of multiple CPE. We have the one from zone E, which is a 1.2, but then we would have the one from zone B, 0.8, and then a zone C. So to take 90% of something, advanced design will first compute an average CPE value on the other face, the one that we open. So it takes an average CPE value, and then it takes 90% of that, and this is how it gets the CPI of 0.64 for this direction. So this is one way of defining, this is one type of opening you can have, where you have a face completely open, but you can also define a certain amount of openings. Let's say you have like 20% opening ratio there. So again, you update the forces, and in this case, advanced design will compute the mu coefficient per direction, and from that it will find out the CPI value per direction. Advanced design can also handle some lattice structures, and these are the ones with parallel chords only, like this one, square or rectangular, or this one, triangular. And in this case, the wind will be generated along a diagonal and then perpendicular to a face. But should you have a more complex tower shape, in this case, we are supposed to refer to Eurocodes 3 part 3.1 in Annex B. Unfortunately, this part is not implemented yet in advanced design. So keep in mind that this feature, lattice structures, is only meant for members with parallel chords at the moment. So if we work on the lattice structure from this example, so it's a member with parallel chords, and it's a triangle shape. So to get proper wind on this building, this structure, first I should make sure that the load area that I've defined on the envelope are given the lattice structure property. And also the elements below, the linear elements under this load areas, should have the same lattice structure property enabled. And then when generating the wind forces, I will get the expected directions. So first of all, I will get the wind perpendicular to a face in one direction and the other, and also the wind parallel to a face in both possible directions. And if we check in the Eurocode 1, these are indeed the directions that we are expected to generate. So in advanced design, all these load cases are created in a single click. Oh, and also know that advanced design will let you define the return period. So this is not a concern for most buildings, which are defined with characteristic values based on a 50-year return period. But should you design a temporary structure or like a scaffolding or greenhouse, which are designed for 10, 15, or even 20 years, then in this case you will want to use a smaller return period, which will lead to smaller wind forces and smaller snow forces, because the wind velocity will be affected by a probability factor which is smaller than 1, and the ground snow load will be also reduced by a coefficient smaller than 1, which are both defined in the standards. So if we get back on the building from before, this greenhouse, up to now I was generating the climatic actions with the characteristic values which are given for a 50-year return period. So I was using the characteristic velocity. But in fact, some buildings like this one are not designed for 50 years, but more like 10, 15, or 20. And if I reduce the return period, it will reduce the wind velocity, and in turn you will get a smaller peak pressure, then smaller wind forces. And you can see the values being updated in real time, because here you can check all the intermediate values, and it works the same with snow. See, we have for 50 years we're using the characteristic ground snow load, but if I impose a 15-year return period, it will reduce the ground snow load. And then when I generate the forces, the snow forces will be smaller, significantly smaller than they were before. Alright, so that's it for this presentation. I hope I gave you a good overview of all the possible structures that you can handle with advanced design when it comes to wind actions and snow forces, from simple shapes up to the really complex ones with openings and snow accumulations and all that. So I hope I kept you interested. So if you have any question or comment, we can interact now in the chat, or you can contact me by email at this address. So in the meantime, I wish you a nice day, and I hope to see you soon. Bye.